My screen is visible.
Yes, sir. Your screen is visible.
Okay.
Just
And
make
that,
it. Yes.
yeah. Now that full screen is visible, that PPT screen.
Yes, sir.
Okay. Before going to real-time simulation OPAL RT, first I will introduce our company and some product of our company. After that, simultaneously we'll go and we'll see some demo on real-time simulator, how to use real-time simulator, and what the necessity of real-time simulator, and what the application of real-time simulator in our electrical domain. Okay. Just 1 minute. OPAL RT is the world leader in the development of real-time digital simulator uh, based on PC and FPGA technology for rapid control prototyping and hardware in loop. OPAL RT systems are deployed for design validation and optimization of complex control system. And OPAL RT is application in various domains like electrical domain, aerospace and defense domain, automotive, academic and research, other industries like uh, electro traction, like that. And our company founded in 1997, and total worldwide employee is more than 300. And our local office situated in Bangalore, and a total 25% of revenue reinvested in R&D sector. And our head office is situated in Montreal, Canada. OPAL RT provides high-end real-time digital simulator, scaling from compact portable device to large integrated agile test. Based on state-of-art technology, OPAL RT systems are powerful, flexible, and scalable. First of all, we know what the difference between simulation and what the difference between real-time simulation, and why we are going to that real-time simulator, what the necessity of real-time validation. First of all, we know what the benefit of simulation. First is the provide with more high-end service, more and more smart system, growing complexity, design safer system, combine many system, limited resources, shorter deadline, and a difficult integration of many complex, smarter, safer system. Uh, Suppose we'll design a one model based on hardware, we'll get error at deliver stage. Yeah, if you will get error at this deliver stage, then at that time to fix that error, that cost is high. If you will get that error at design state, uh, to fix that error, that cost is low comparison to this. So that's why we are all, choosing simulation platform to uh, design our model. And in 2003, Northeast blackout of in through 2003, between 2 days and one week to restore that power. Total affected people 55 million people, and estimated cost $6 billion losses at that time because of software bug in alarm system at a control room. But the different, if you will test in the field, will directly validation our model or controller in hardware. And what the disadvantages? First is the difficult to handle because it's a logistic problem impact. And the second thing is that expensive is high. And third one is the sometimes hazardous. Suppose if you have a battery management system, if we want to test our battery in real platform. So at that time fault detection. So it's not possible in real because of it's very hazardous. So we will test in our simulation platform. And the simulation tools allow verification all along the project, early detection of error, and almost infinite test capability. And third one is your cost will be reduced and time will be reduced also. And also risk will be reduced. Every model like physical model, algorithm, code-based model, and state diagram, power system model, every model we have need to design in our Simulink based, and after that we will dump in our real-time simulator. First, we have need to design our model in Simulink. After that, we'll dump our model in a real-time simulator. After that, we can interface some controller, yeah, hardware, yeah, we can see our result in DSO, and we'll get feedback to same from controller to our model using this simulator. That's we call hardware in loop. It is the procedure to work real-time simulator. Here is the fourth thing is main important. One is the model in loop. Just 1 minute. First is the model in loop. What is model in loop? In every model, we have one plant and one controller. In model in loop, your plant and controller it should be placed in your real-time simulator. So here, your suppose one example. This is your inverter, and this controller part is your PWM. In this case, your inverter and PWM both are placed in real-time simulator. That's we called model in loop. And the second one is your rapid control prototyping. In this case, your plant is real and your controller is it in simulated. So in a rapid control prototyping, this inverter is your real inverter, and you dump your controller in a real-time simulator, and we interface this inverter to this controller. That's we called rapid control prototyping. Again, in rapid control prototyping, your plant is real and your controller is it in simulator. So that's we call rapid control prototyping. And this opposite, yeah, vice versa of hardware in loop is your controller is real and your plant is it in simulated. So that means your inverter is it in simulated and your controller is in real. You have need to PWM generate from outside, and here is your inverter. We'll give PWM from outside to the inverter. That's we call hardware in loop. And this is the power hardware in loop. In this case, suppose one example grid connected microgrid. In grid connected microgrid, your grid is it in simulated, and your we can interface this simulator, that means this grid, to real microgrid using power amplifier. Because of our real-time simulator, that output is maximum plus minus 16 volt. That's why we have need to use this power amplifier. So after that, it should be easy to interface grid to real microgrid. And fifth one is your uh, control hardware in loop. In this case, your controller is it in Texas C2000. Some controller design, you design a controller in using some microcontroller, and your plant is it in a simulator. That's we call control hardware in loop. These five things is most important. First is your model in loop, and the second is your rapid control prototyping, and the third is your hardware in loop.
लेना है सामान आप नहीं लीजिएगा जैसे आपको यहाँ पे
And the fourth is your power hardware in loop, and the fifth is your control hardware in loop. Any question? Hello? Any doubt on this five concept?
Yeah, it's fine, sir.
Okay. And now we have need to know what is real time, what the necessity of real time, why we are using this real time simulator. And first, real time that does not mean a faster. Real time means it will give good result at right time. Some example, in our electromagnetic transient, it will be run at a microsecond, and for mechanical time response, it will be run at millisecond. And your temperature control, it will be run at a second. So what the basic concept of real-time simulator, why we are using this? Suppose suppose this is your simple power system model, and this is your real relay system. It's a hardware relay system. Suppose our model is it run in our Simulink. We are using some microcontroller, and we take this relay signal given to relay, and a relay will give signal to circuit breaker. In our MATLAB, in our Simulink to study, our stop time is 10 seconds. Suppose our stop time is 10 seconds, but it will take more than 10 seconds, like 20 seconds, 30 seconds, 15 seconds, like that type of. Okay. So what happens if you will run in Simulink? Suppose if we'll create a fault. So fault created at 3 seconds. Okay. And at 3 seconds, it will take to time 6 seconds. And the relay will give signal instantaneously because it's a hardware. So if relay will signal at instantaneously like 3.1 second. So circuit breaker will be detect after in real time after 2 seconds. After 2 seconds, circuit breaker will be detect that fault relay signal, and the circuit breaker will be open after 2 seconds or 4 seconds, like that. So it's not a real time concept. It's your basic Simulink concept. So if we'll be using this simulator, real time simulator means it will be synchronized with your wall clock. Suppose your stop time is 10 seconds, that means it will be running like 1 second, 2 seconds, and it will be stop exactly 10 seconds. So suppose in this power system model, is it in your real time simulator? Okay. And in this case, we'll create a fault, but instantaneously your relay will detect that fault, and same time, and it will give signal to circuit breaker, and at 3 seconds your circuit breaker will be open. Fault was created at 3 seconds, and your circuit breaker it will be open or close at 3 seconds. So your delay is reduced. That's why we are going to using this real-time platform. Any doubt, any question on this concept of real-time? If you have any doubt, I will explain it again.
So participants are requested that if you have any doubt or anything, you can ask by unmuting yourself. I have allowed, or if somebody is left means you can raise your hand. I will allow.
Up to here, any question?
Sir, suppose our plant is in a Simulink model MATLAB, and controller also is in MATLAB. Just if we dump this thing in the OPAL RT, can we tell it is a software in loop or model in loop?
No, it's a model in loop. Yeah, this is a model in loop. Your plant and your both controller both are placed in your simulator. Okay, that's we called model in loop.
Yeah. Suppose that our control algorithm is in MATLAB, and along with plant also is in MATLAB. In that case, we have to call it as model in loop.
Yes.
Suppose if we get the output in DSO, then in that case, how we can convince that a reviewer or so that
at that time in DSO we'll see only result in DSO. We are not interfacing anything in our real-time simulator. Am I right?
Yes, sir. We are not interfacing anything.
Actually, many more thing is calling this is a hardware in loop. Actually, that is not a hardware in loop. This is a model in loop. In hardware in loop, your controller should be real.
Yeah. Yes. Maybe like Arduino or Raspberry something else.
Whatever you want to use. Suppose you use Arduino and your model in plant in simulator. That's we call hardware in loop.
Okay, sir. Here, what I would like to ask is, suppose we got some curve in the MATLAB. If we simulate it in MATLAB, we'll get some curve. And if we simulate it in the real time OPAL RT, then we get the waveform in DSO. So in what sense we can tell that both are having some difference?
Okay, same thing I was discussed here. And what the stop time? Suppose your stop time is MATLAB is 1 second. Yeah, 10 seconds. Okay.
Yes.
In real time, yeah, actually how many time it will taken?
Okay, you mean to say that it will try to synchronize with the real-time clock in the real-time simulator?
Yes.
Whereas in MATLAB, it is like whatever time we define at fixed sample rate, that will take into.
Yes, and here I explained what the difference between why we are using this real-time simulator. Okay, are you understand this concept?
Yeah, I understood clearly.
Okay. I'll proceed next.
Yes, please, sir.
Sir, one more question, sir.
Yeah. Hello.
Hello, sir.
Yes.
So one my question in this one, when we have to connect from real time hardware, we have to sense from the power conditioning circuits voltage and current. 4 voltages, 4 currents from grid side, source side, etc. And DC link voltage through the sensor's output. And how many number of ADC and DAC in this one, OPAL RT, sir?
Okay. We'll discuss in next slide in next PPT. Okay.
Is there that limitation of how to with the help
Yes,
of
it's depend on your model. What's your model?
model is that is inverter integrated?
No. Depend on your OPAL RT model. If your 4510 model or 5600 model, it's fully depend on your model.
Okay.
Okay. Okay. That thing I will discuss in next slide.
Okay, sir.
And okay, in this case, again, what the concept of real time? Again, one concept. Real time always run in fixed sampling time. Why it's run as a fixed sampling time? Why not in a variable sampling time? And please note down this question. We'll discuss in next slide. Okay. And suppose our fixed sampling time is like this. So in this fixed sampling time, it will measure something and computing your data. It will computing like your measure current and voltage, and it will computing and it will generate PWM signal, and it will give some command like to your analog out, yeah, analog in, yeah, digital out, yeah, digital in. This thing, it will be happen within this fixed time. That's we call real time. If same thing, it will be exceed done fixed time, then overrun will be detected. So it's not a real time because this fixed time, yeah, this sampling time will be dummy. And then again measuring part and this part will be start from third sampling time, and second sampling time will be dummy. So this case is not a real time. So in this case, we have need to increase our fixed time. Suppose our fixed time is like this. So it will be run at a real time. So how can we know our model will be run in this fixed time? Yeah, overrun is detected. We'll see in monitor probe controller. We'll see in overrun is it detected or not. At the demo time, I will show you. This is our different type of model, and this is your OP4510 simulator, and this is your 56 or 5700 simulator. How real-time simulator, yeah, OPAL RT real-time simulator is working? First, you have need to design your model in host PC. And communicating between host PC to real-time simulator, we are using Ethernet or TCP/IP communication. This is your Ethernet. And there is a multiple core CPU. Why we are not using dual core CPU? Why we are going to using quad core CPU, yeah, octa core CPU like that? It's a one question. Please note it. I'll explain it. And the CPU will give a command to your FPGA, and FPGA will managing your IO card, which pin will be give this result. And for this FPGA, some code is required that we call bitstream. And this is our different software packages. And first is your ePhaser SIM. It's only for power system. For validating your more number of IEEE bus will run at some millisecond. Like we'll validating our 17,000 IEEE bus in using this ePhaser SIM. And this is our software. This is our one package, license package. This is our software, which was designed OPAL RT and Hydrocubic. And this HyperSIM, we can use power system model, grid connected microgrid within 25 microsecond to 100 microsecond. And this is our eMegaSIM. In eMegaSIM, we can use power system and power electronic simulation within 10 microsecond to 100 microsecond, that time sampling time. And this is your FPGA sim. In FPGA sim, we can direct dump our model in FPGA. That sampling time is 1 microsecond to 100 nanosecond, and that switching frequency is 200 kilohertz. But at normal real-time simulator, that minimum sampling time is 10 microsecond, and maximum switching frequency is 10 kilohertz. Okay. Again, any question? Hello, any question?
No,
Okay,
no, sir. Sir, is this HyperSim, eMegaSim, eFPGA SIM? All these are a subsection where we can get to block sets power systems, right?
Just a minute. In e-phasor sim only for power system, because your power system like IEEE 17,000 watts. Okay, that computation time is more. Suppose here this computation time is more than 2 seconds or 3 seconds. How it will be run in real-time simulation? Is it possible?
No.
So we have need to reduce that computation time. So that case, we have need to use this ePhasor sim. HyperSim, it's a separate software. In HyperSim, we have no need to buy one simulator. Yeah, this software always run in real-time platform. No need to connect digital simulator, real-time simulator. Okay.
Okay. Okay.
And this is only for IEEE boss. Okay. And this eMegaSim, suppose you want to microgrid IEEE 39 connected with solar PV. How is it possible? For this case, some power electronics device is required.
Yeah.
So that case, we are using eMegaSim. And this is your FPGA sim for power electronics device. Switching frequency is required more switching frequency like 100 kilohertz, 50 kilohertz, like that. So for this case, we are using FPGA sim. Okay.
Okay, sir. Noted.
Okay. First, what the procedure? Here I will say you simultaneously
Hello?
some demo in RT Lab. Yeah,
Hello.
tell.
Am I audible?
Yes, yes.
Sir, my question is, it's from the previous slide you have shown. My question is that suppose I'm building a model in MATLAB, right? And
Okay.
it is power electronics based. Fine.
Okay.
So from which screen I would be able to see the that this is eMegaSim, this is HyperSim, this is Phasor, or this is FPGA sim. So whether if I'm converting the model, it is running successfully. If there is any logo, or we will be able to see that from the monitor that it is working in this.
Which package are you using?
Yeah. This is
Okay.
my-
For simple RTLab package, you can go, there is some limitation. Okay. So
Okay.
in ePhasor sim, I will discuss in day after tomorrow what is ePhasor sim and what is eMegaSim. In
Okay.
ePhasor sim, it's like you know that PSSC.
Yeah, I understand that ePhasor sim is for electromagnetic transients, and it is
Yes, yes.
so it's fine. There is no problem in that. My simple question is, suppose I have burnt the model, I have made the model, and it is running fine. So how I'll be able to see from the screen itself that this is eMegaSim or eFPGA or HyperSim or ePhasor?
So according to depend on your block. For
Okay.
eMegaSim, there is a separate block. For
Okay.
EHS, there is a separate block. HyperSim is fully different software, not
Yeah, this you
MATLAB.
have already explained. Yeah.
Yeah.
Fine.
And this ePhasor sim is based on your Excel format.
Okay. Just when you are coming on to that particular slide, just tell me that this is the block where we can see that this is Emega sim or whatsoever.
Okay,
it is.
okay. I'll show you.
Thank you.
To running our real-time simulator, we are using RTLab. So first we have need to design our model using OPAL RT library in MATLAB in Simulink. After that, we'll import our model in RTLab, and after that we'll dump execute our model in real-time simulator. So already discussed this thing. This is your host PC and it's communicating between host PC to real-time simulator using TCP/IP, and this FPGA using for managing IO card and multiple core. Why we are using this multiple core?
Maybe like if you want to have a handshake acknowledgement between two cores, then we require multiple cores.
No. I'll explain here.
Yes.
In your model, there is a one display part. One is your main model, that is we call computation part. Okay. In computation part, we'll place everything in computation part. In display part, we'll place only display, scope, and variable switch will place in this PC. Okay. It's for graphical interface, GU, get graphical interface user, for display. What's your result you can see in your display. For this case, we are using this PC. That means this core. Okay. And for this, whatever your model is running, that time we are using real-time simulator core. Suppose we have 4 core PC. Okay. 4 core PC. One core is dedicated for RTLab, and another 3 core dedicated for depend on your model. If your model is more complex, so that time you can use this core and you can use this core. For this case, we have need two subsystem. One is console. Console means it will run in your host PC, your laptop, in your PC. It will be run. And master means whatever will place in master, it will run in your real time simulator. Then how can we run in this? One is for RTLab, this one for master. Okay, then how can we import our model in this core and this core? First, you have need to make subsystem like that. That subsystem name should be like SC underscore any name, SM underscore any name. SM means master, SC means console. So RTLab, master, and these two we called slave. So that subsystem name should be like SS underscore any name. Okay. First procedure, we have need to design our model using RTLab library. In designing stage, we have need to make 2 subsystems. One is console, one is master. This thing is main important. Okay. And after make your subsystem, master and console. Next, we have need to create our target. I'll show you one thing. Yeah, my screen now visible now. This OPAL RT picture.
Yes, sir. It's visible, sir.
Okay. This is your OP4510 version, and here is your power button, reset key, and power LED, hard disk LED, NC1, that means Ethernet 1, yeah, and Ethernet 2 LED, and power fail LED, overheat LED. And this is your SFP communication, and this is your IO card, what we'll use. And just ignore this IO card now. We'll explain in afternoon session. And this is your Ethernet port that we call NC1, NC2, yeah, Ethernet 0, yeah, Ethernet 1. Okay, we have need to connect from here to your host PC. Yeah, you want to use this simulator in network, so you can place this point to your network, and you will take Ethernet cable from your network to your host PC. So that's we call network communication, and this to direct to your host PC, that's we call one-to-one communication. Okay, in one-to-one communication, suppose you connected from here to your host PC, and this simulator have one IP address. See, this IP address mentioned is here. So you can change this IP address. Then okay, suppose your simulator IP address is like that, 192.168.10.101, and your host PC IP address should be different, like mean 192.168.10. Excluding 101, 102, 124, like that type of. Okay, this is your communicating between real-time simulator to your host PC. After that, you have need to open your real-time simulator. This is, sorry, RT lab. You have need to open RT lab, and you have to create target. First, your simulator is connected with your host PC. Then how can we using this simulator in real-time simulator? So that means we have need to create a target. So I show you, open in RT lab. After connecting your real-time simulator with host PC, you have need to check is it pinging or not using this IP address. Your simulator IP address, ping space -t. Now my simulator is pinging here. Then double click to discover target, and this is your and now your target is created. Okay, and second, we have need to set as a development node always. So it's a one procedure. Sometimes it will not work. So we have how to create target. Another one procedure. Right click on target, new target, and suppose you want to OPJU target name and IP address 192.168.2.143. Is it pinging? And your target is created. Okay. So after create our target, then we have need to create our project. When I'll open your RT lab, you'll see. I can add. This is your path. When first you open your RT lab, this is your path. Your project will be saved here. Okay. First, we have need to create a one project. Create a new project, and your project name is RT1. Next, and here is your some basic example RT demo 1. You can choose this RT demo 1, then finish. I'm going through this PPT because this PPT will be helpful for your next whenever you are trying to use the real-time simulator. Okay, now your project is created, and after create your project, we have need to go this arrow, this small arrow of left side of this project, yeah, RT1, then this arrow, then this project, and your project is create here, this arrow, RT demo 1. Suppose I want to edit this model, so double click on this and you can edit here. Otherwise you can edit one minute. Yeah, you can edit here. It will be open your MATLAB model. We'll see where this RT1 will be saved. According to our default path, it will be saved in go to C and user. This RT1 is saved in your path. Okay, it will be open. We'll go forward.
Excuse me, sir.
Yes.
So I have a question. Suppose I am working on rapid control prototyping,
Okay.
and for that I have designed a control strategy in MATLAB Simulink.
Okay.
But that control strategy runs on a script file, which it is reading from the workspace of MATLAB.
Okay.
So how to include that script file in the model in RT Lab?
Okay. That script file is it in .m file, na?
So it can be any kind of script file. Like for NFIS controller, it is FIS file, FIS file.
Okay, okay. That FIS file, that means fuzzy controller, no?
Yes, yes, sir.
Yeah, yeah. Actually. Next, I'll go forward at the time. This is a simple example model based on like SM computation or any name and SC any name. So in SM, your it's a simple PID controller. In SM, all computation, yeah, all model is it in place in SM. In SC, your scope and whatever I want to change at the time of execution, I will place in SC part. Okay, at demo time you will understand this thing. Why this constant, this adjustable reference placed in SC part. Okay. So after this is a example. After open your example, create your project. Next is your build. That means build means it will convert it to your simulating model, to your MATLAB model, to your C code. So build. How can I choose this thing? 64 ways, yeah, 86 ways. At that time, create your target. I show you again. This is our 86 ways. That's why I'm choosing here 86 ways. Execution 86 ways. And build. That means your model will be converted to your C code. Okay. After that, we'll load this code, yeah, that model in our real-time simulator. Then execute our model. That means our model will run in your real-time simulator. Then reset it. Already discussed this thing. And next, if you want to import your model, existing MATLAB model, how to import your existing model? Suppose create a new project. Your project name is like RT2. Next, at that time you have need to choose this empty one. Then finish. Here your project is created. Then right click on model, import existing RTLab model. You can import your existing RTLab model. This thing mentioned in your this PPT. After that, I will share you this PPT. It will be helpful for you. First, grouping into two subsystems. One is master, one is console. In here making one subsystem. In subsystem one, place this thing. Okay. Here is one question: why they are not placed this constant in master? Why they placed this constant in console? They want to varying this constant at the time of execution your model. That's why they place this constant in your console part, and this thing they placed in master part. This model will not run in real-time simulator. We have need to make subsystem like SM, SC. Suppose your display या scope is not required to visualization your result, so you can use only master subsection. How to make subsystem like this? This computation part, and this is your graphical user interface part. This green, this two is placed in SC, and this thing is placed in master. And whatever you place in SC, it will run in your host PC. And whatever you place in SM, it will run in your real-time simulator. In SC, that name should be like SC underscore any name. In SC, we'll place scope, display, constant, manual switch. But in SM, we'll place, excluding this thing, we'll place in SM. SM name should be like SM underscore any name. And here is your another one subsystem is SS slave. Yeah, SS. That means slave subsystem. Suppose your model is more complex, it will not run in your single CPU. So at that time we have need to use this subsystem. So for the another one core. One core is for RT lab, one is for master, another two for slave. If your master, suppose if your master is full, that means this processor is full, then at that time we'll use this slave, two slave. So in your model, always make like using this mux or boss selector.
Sir, how to ensure one core is saturated? We should go for slave like that.
Yeah, at the time of demo, I'll show you. Please note down this question. Okay, at that time demo, I'll show you how to see our performance time is exceed. Yeah, that is full. One core is full. Okay.
Okay.
Always using boss selector and mux. Not using like this because your model looks like very complex model. Okay, up to here, we are connected our host PC to real-time simulator. First thing. After that, we'll design our model. One is SC, one is SM. Okay. SC means your host PC. SM means your real-time simulator master. And in hardware, is it communicating between TCP/IP or Ethernet cable? But in software, we have required one block that called OPCOM block, OPCOM block. This one, it will be available in your library, RT lab. I show you. When it will open, I'll show you where is that upcome block. Upcome block, it will be used after your input in block. It will be used always after your in block. This type is not working, and this type it will work. This block used for communicating between your SM to SC. Suppose this is your SC. This is your master SM, and this is your SC. SM gives some data to SC. That time, data received from SM side. That time here we'll use upcome block. Suppose SC gives some data to SM. Here we'll use upcome block. After input, this is your in one subsystem. This is your in one. After input, we'll use this upcome block. Like this. SM computation SC, and this is your communication. After input, we are using upcome block, and this communicating from SC after input. Just remember this point. Always it will be connected after your input. And suppose if is your multiple subsystem case, and this is your blue line is your asynchronous TCP/IP signal. This blue line is your TCP/IP signal. That means signal is coming from SC. So at that time we are using different OPCOM block, separate OPCOM block. And if your signal coming from SM or SS, that time we are using one. For this case, we are using another one OPCOM block. This case we are using another one OPCOM. OPCOM block is available in your library, only one OPCOM. After naming your subsystem, it will detect in SC side, it will show acquisition, and your SM side, is it show your sampling time, your like that, whatever you give your sampling time.
Sir, is it
Suppose
like Opcom is similar to data conversion in MATLAB? Is it?
no, not the data conversing. It is the similar like only communicating between your host PC and the real-time simulator.
Okay.
Okay.
Sir?
Suppose hello.
Excuse me, sir.
Yes.
Sir, is this OPAL RT is limited to only simple control strategies, or it can also be applied to more complex control strategies?
Can you explain me what is your simple and what is your more complex
So
control
simple
strategy?
is I am referring to the PI control, and
Yes.
for complex I am referring to reinforcement learning controls.
Yeah. You can use it complex control system.
So according to the process that you have mentioned here, so my reinforcement control strategy works on a file which is available in the MATLAB workspace.
Okay. Okay. Whatever you are using controller, but the output of your controller.
So actually, it is picking up an agent which is available in the MATLAB workspace. But in a SM, we can only include the data which is available in Simulink model.
Okay, your model, there is no Simulink model, only coding, na?
No, sir. I have a Simulink model, but in my
Okay.
Simulink model, there is a block which is linked to the MATLAB workspace.
Okay,
So
to
if I,
workspace block.
yes, sir, if I convert it into SM and SC, so that how to include that link to the which it is reading from the MATLAB workspace, how to include that thing in my SM?
Okay, this part, is it your computation part? Yeah, is it your display part?
The computational part it is.
then you will place in master. Okay, first thing.
I will place, sir. Yes, sir.
Yeah, then second thing, how it will be called, no?
Sir, how it will be called from the MATLAB workspace?
Okay, you are using these two workspace. One thing. Another thing, I'll show you how to script your MATLAB file.m file. Okay, it's a simple concept. In model properties, you will go and in preload function, you will place that file name. It will call.
Sir, can you show it how it is done?
I'll show you. Don't worry. I'll show you. Just be patient. Okay.
Means you are telling in model properties we have a pre-function call.
Yes,
There,
yes.
there we have to declare the
Hmm.
.m file.
Yes. Okay, and this is your SM and this is your SC, and your output is depend on your input. So this is your maximizing parallel execution case. Sorry, this is your serial execution case. So this at that time algebraic loop will coming. So for this case we have need to use like this block, like delay, memory, one gain, like this type of. This is your best case, fully parallel execution. We are using one memory and this output, this input, and this output, this input. This is your parallel execution. For this case, you have need to using this memory or delay or gain. Real-time simulator always run in uh, fixed step solver, not in variable step solver. I think it's open. Where is that outcome block? You have need to go this RT lab. This is your outcome block. We'll place outcome in your SM part. Same outcome block here. That sampling time is showing, and this SC, and there here acquisition is showing. This is the communication from we want to change this adjust reference at the time of model execution. We'll change it, and this signal will going to your master. So this is your master input. After input, we are using this outcome block. Okay. And here is your console. After input, yeah, your display result, yeah, scope result. After input, we are using this outcome block, and after that, we will see in display. Okay, why we are not using variable solver in a real-time simulator? Why we are using fixed time solver at real-time simulator? See, suppose your solver is variable. At this transient time, your sampling time will be varying from some microsecond or some nanosecond. Okay, if your sampling time is like 200 nanosecond, then how it will be run in a real-time simulator? Because real-time simulator, that minimum sampling time is 1 microsecond, but we are recommended to use it at 10 microsecond. But it's not possible at some nanosecond. That's why we are using fixed sampling time. Okay. And why we are always recommending to go lower sampling time, not bigger sampling time. Suppose this is a one signal, okay, and we take this sampling time. This is your sampling time. After joining this sampling time, yeah, connecting this sampling time, this result is coming. This result and this result is different. So bigger sampling time is less accurate, and less sampling time, smaller sampling time is more accurate. See, here is your smaller sampling time. This is your smaller sampling time. And after we joining this point, and this one is similarly same. So here is your smaller sampling time. Smaller sampling time will give more accurate. Okay. First is your to design your model SM, SC. After that, we will place outcome log in SM or SC. After that, we have need to change our sampling time, solver type to variable to fixed type. Where this option is available, let's see. Go to model setting. We have need to our solver type like fixed and not automatic solver selection. Always we have need to select discrete OD8, OD5, whatever according to your model. You have need to select it. Don't choose this auto one. And here you have need to place your solver time, sampling time, fixed step size. You have need to put here. After that, okay. And here is your another one option. You have need to go model configuration. Model configuration parameter. You can do it here. Here, one option is your optimization option. Just note down this point. Suppose we are using one sine wave. Okay. At that time of your model is executing. So I want to change this sine wave frequency. How can I change it? No need to reset your model. In this case, you just open this SM part. Suppose this is your sine wave part. To open the sine wave part, and you have need to go this gain, and at that time you will change this amplitude or frequency, whatever you want. You can change at the time of execution of this block property. You can change it. Okay. What to do? First is your create subsystem. Second is your rename subsystem like SC, SM, SS. And third one is your add outcome blocks inside SM, SS, SC, and then fourth one is your solver time, fixed solver, set the value of TS, and stop time should be infinity. And the next procedure is your build the model. Build means your model, it will be converted to your C code. Here we have need to change it. One is your simulation mode, simulation with low priority, software synchronized mode, hardware synchronized mode. Simulation mode means as fast as possible, and simulation low priority mode as fast as possible. Mode for Windows target, it will be run your Windows target, and these two is important. What is software synchronization mode and what is hardware synchronization mode? In software synchronization, in this model, we are not using any IO card. Okay, that time we can use this software synchronization mode. In hardware synchronization mode, suppose you want to interface your real-time simulator with some hardware, that time you have need to do this hardware synchronization mode. And here is your one option. Always you have need to check this XHP, extra high performance. So that means it will be reduce your jitter. Without XHP, your jitter is like this, 80 microsecond. After using XHP, your jitter will be reduced to 0.2 microsecond. Next, you have need to load your model. Here is your load option. Whatever your model is converted from your simulink to your C code, you have need to load it in your real-time simulator. And third one is your execute your model. Here you will execute your model, and after that you have need to reset this model. And execution performance we'll see in monitor and this plus like probe control. So you monitoring this probe control will show our system performance. If your performance is like 100%, suppose your system performance is 100%, at that time we are going to use next subsystem SS. Okay, someone asked me how can we choose SM and SS. Hello.
Yes, sir.
Okay, your doubt is clear. Yeah,
Yes,
we'll
sir. It's
see
clear.
here. Yeah, at the time demo, I think it will be more clear.
Okay. Sir, how many SS we can declare, sir? Like only one or?
No, SS na?
Yeah, slaves. How many slaves we can?
It's depend on your real-time simulator model. Here, our real-time simulator is OP4510. Okay, that case your core number of core is 4 core, quad core. If
What
you
about
are using OP5600 or 5700, that time your number of core is 8 core. You can at that time of purchase this simulator, you can configure it that number of core. If you're 8 core, then you can use it number of 6 slave.
What about in OP4512, sir? 4 or any?
No, 4510, that next version is 4512.
So they're also 4 core, right?
Yeah, 4 core. You can use one master, 2 slave.
Okay, noted, sir.
Okay. And also we can see here our execution time, computation time, idle time, and total sampling time. We can see in this monitoring tab. And also we can use this execution performance block for to seeing computation time, real step size, idle time, no overrun. What is idle time? This is your fixed time and this is your computation time. Remaining this time we call idle time. So at that time we will reduce our fixed time. Suppose this time your fixed time is 100 microsecond. This is your 100 microsecond, but that measuring and computation and command, 3 things will happen in 10 microsecond. But why we are taking this 100 microsecond? So that time we have need to reduce this sampling time to 10 microsecond, 20 microsecond. Okay. Okay, we can declare our value. Like suppose this is your KP, KI, KD value. We'll KP like this. We'll declare this value. That KP name like this KP, whatever you want in alphabetic name. After that, we can drag and drop here. We can change that value at the time of execution, this KP and KI value. And if you want to save this parameter, suppose you want to change tuning your PI value. At that time of running, you can change this PI value. Suppose your PI value is 5 and 20, you want to save it, then go to camera, this camera icon, okay, then save this parameter, then your parameter will be saved. Okay, here is your question, how to call this thing? Yes, this script, how to call this script in our Simulink model?
Hello, Neeraj sir.
Yes.
Can you take 5 to 10 minutes break for the participants?
Okay.
So we can meet now 11:25. We can meet at 11:35.
11:35.
Yes.
Okay.
Thank you.
Okay.
If the participants have any question, please write in Q&A. So when the session starts, I will ask the question to the speaker. Okay. Thank you.
Sir, my screen is visible, no?
Yes.
Okay. How to call this M file, your script file? See, right click on your model properties, preload function. Like suppose this is your .m file, you can call it. And suppose you want to call some, like your sampling time, like TS equal to 5 microsecond or 10 microsecond, you can call like this type of initialize function. Like here you can call TS equal to 10 microsecond. You can change here the sampling time. Here you can call your .m file, MATLAB file. Okay. Someone asked one question: how to call your code based model, na?
Yes, sir.
Okay. Your code, that means is it in M file?
Sir, basically it is a structure. It is an agent file.
.mat file.
Sir, it is not a MATLAB, like not a MATLAB script. Basically, my model is called in a MATLAB live script, MLX file, .mlx file.
Okay.
And also in between the model blocks, some files are been called.
Okay. Actually, I have need to take time to see your model in AnyDex. After that, I will understand your model and I will explain you.
Okay, sir.
Okay. Okay. Next is your OP write file. Whatever we see in our scope, SC console part, some error will be coming because due to of that communication between Ethernet cable. In that Ethernet cable, some resistance capacitance is there. So some error will coming in your console part. So to reduce that error, we have need to use increase that sampling value. Here is your sampling value. You have need to click this one. this one, after opening, you can go up to your maximum number of samples per signal is 10 lakhs, and the number of samples per signal you can go up to 10 lakhs. After clicking, you can see your good result in console part. But after resetting your model, your console part, that result will be lost. Suppose you want to store your result and you want to paste your result in journal, yes, journal paper. So how can we store our real-time result as a MATLAB figure? So for this case, we have need to use this OP write block. In OP write block, it will be save your like this .mat file. Your result will be saved in your .mat file. Suppose your signal 1, 2, 3 up to .n, and your this is your sampling time. Sampling time 1, 2, 3, sample 1, sample 2, sampling 3, and this is your signal 1, 2, 3 up to n. This is your discrete value, yeah, sample value of signal. Okay, it will be saved in your .mat file. After you have need to plot using this sample one and this signal one, you will be plot your result, real-time result. Always you will put this OP write file in master part. If you put OP write file in console part, then you will get not a real-time result. You will get a result of your console which is run in your host PC, not in real time. So second is your OP trigger block. If you want to see your result up to 5 seconds, up to 1 second, at that time you use this OP trigger block. And after that you will plot like this, and you will get your real-time result in MATLAB figure .fig file. This record. Okay, another one feature is above your RTLab is above 16 RTLab 2016 16 version, and you can get this feature LabView panel. What happened in LabView panel? See here, one LabView panel is open of our demo model. In our demo model, suppose I want to change KP, KI value like this. You can see your result here in LabView scope, and you want to change this value. But the feature, why we are using this thing? Suppose you are connected with your controller in your real inverter. So you want to change your modulation index. So at that time of execution, you can change your modulation index like this, 0 to 1. You can change your modulation index, and you can see your output voltage of your real inverter. So how to create this panel? So after create your project, there is a one option, panel, new panel. After new panel, your this LabView display will come. See, RT2, suppose right click on panel, new panel. Next, finish. And now your panel is created. So how can we import our value in this panel? So suppose, actually I have placed something. This drag and drop. This you can change your. You can use this LabView panel. Your signal drag and drop here. After that, you can sliding this signal value. You can use this LabView panel. Okay, this is your based on your whatever I told you. This is basically based on your software synchronization mode. That means I am not gone through that hardware, how to use that IO card, how to use that IO card, how to interface your simulator with your hardware. Not gone through that thing. Any question on this thing? Hello.
Is this LabView feature is available in older versions of RT Lab also?
Your version, older version means version name?
Version
10
name
point.
like from 2015 onwards.
No. Onwards 2016. I think someone turn on his mic. Please turn off his mic. Okay. Any question? Yeah, we'll go for hardware configuration.
But till now, no questions, so you can proceed.
Okay. Whatever I told you, that is the based on RT Lab. Now we are going through your hardware real-time simulator. This is your OP4510. What the difference between 4510 and 5600 and 5700? And this is the low cost and compact and portable to you with quad-core processor and full compatible with larger simulator. 4 IO modules. If you go through 5600, there is up to 32 active CPU Intel Gen core. You can expand it. You can take it 8 CPU core. If in future you can expand it up to 32 active CPU core. Okay, and in 5600, your IO card is 8 IO card. Here is one feature. You can connect from here to here through Ethernet cable, and you can see your result in DSO directly using BNX cable. And this is your 5600. All feature same as 5600, but here is your FPGA capable of 8 IO card, FPGA SIM modeling. You can do here FPGA SIM modeling and additional expansion. And this is your architecture of component of OP4510, yeah, 4512 model, and it's your top cover. And this is your carrier board which keep this IO board, and this is your FPGA. Sorry, it's a 5600, and this is the top section. It's a carrier board cover, and this is your bottom section. And this is your architecture port. This is your RJ45 yeah, BNC monitoring interface. You can connect here to here. Pen is not. You can connect from here to here. You can direct see your result in DSO. and this is your OP 4510, and this one is your SMPS, and this one is your CPU, and this one is the RAM, and this one is the FPGA, and this is the IO card, analog in, analog out, digital in, digital out IO card, and this is the FPGA card. We are using this FPGA to managing IO card. Suppose we give one sine wave signal. Which channel will give this sine wave result? Which slot will give this sine wave result? This thing will managing this FPGA. This is the analog card and analog output and analog input. For analog output, that voltage range is plus minus 16 volt. But in analog input, that voltage range is plus minus 20 volt. This is the maximum output voltage of analog out. This is the maximum input voltage of analog in. So in analog out, in single card, total number of output is 16. And for same thing for analog in, and for digital out, total number in single digital out digital card, total number of output is 32, and the total number of input is 32. But in digital output, user defined voltage is required from 5 to 30 volt. And for digital input, that flexible voltage, that PWM voltage would be 4 to 50 volt. And there is one subsection. Yeah. Suppose you have one analog card, one digital card. That means one analog out, one analog in, one digital out, one digital in. In one analog card, first is your slot. Which slot? Slot means its slot will be decided is your analog digital. Second is your module, 2A or 2B, A, B, C, D, like that type of. Third one is your subsection. Just main thing is your subsection. Suppose in your analog card, total number of output input is 16. In subsection, first subsection, we have need to take in 0 to 7. That means 8 channel we can use. In second subsection, we can use 8 to 15 channel. That means same 8 channel. In each subsection, number of channel is 8. Okay. So for this connector, this is your IO card interface. 1A, like 1A, 1B, 2A, 2B. I don't know which one the analog, which one the digital. How can we know which one the analog, which one the digital? Okay. For in 4510 model, one means digital, 2 means analog, A means slot A means is your input, B means output. Here is your A means input, B means output. For digital out, number of channel is 32. That means number of subsection is 4 subsection. In one subsection, 8 number of channel. So in 32 channel, total number of subsection is 4. Here is your subsection 1, subsection 2, subsection 3, subsection 4. 0 to 7 is your subsection 1, 8 to 16 is your subsection 2, and 15 to 23 subsection 3, and 24 to 31 is your subsection 4. Same thing in digital in and digital out. But in analog out, in analog in, total number of channel is 16. Then 0 to 7 is subsection 1, and 8 to 15 is subsection 2. Same for analog in, analog 2. These two is your dummy. In future, you can expand it as a analog in, as a analog out, as a digital in, as a digital out. In future, you can expand it. This two is your dummy. Okay, and this thing is main important to use IO card. So please note down this point. If you have any question, you can ask me. Main confusion point is the subsection. So for digital output, user defined voltage is required 5 to 30 volt. User defined voltage is required 5 to 30 volt. Whatever we given this user supply, suppose your user defined voltage is 12 volt, then you will get output like 12 0, not a 1 0, 12 0. It will be multiple with your user defined voltage. And another thing, everyone have this white color, white binding book. In this thing, we are mentioned your IO card details. Like, see, this is your subsection 1A and subsection 1, subsection 2, subsection 3, subsection 4. You just take a screenshot of this. At that time demo, it will be helpful. Take a screenshot this one. Okay. And your system description is mentioned which one is your analog card, which one is your digital in. In digital in, this is your 1A. For digital in, that user defined voltage is not required. And this channel number is mentioned. I show you one thing.
Karthik? Hello? Karthik? Sorry, continue, sir.
Just a minute, I am connecting with my mobile.
Hello? Karthik, do you want to ask something? Your voice is not audible actually. Hello? Otherwise, you can type in the Q&A session. We will ask for you. Neeraj sir, you can continue, sir.
Yeah, but I'm connecting.
Okay.
This video is coming.
No video is coming now. OPAL RT screen, OPAL RT technology screen is there.
Okay, I have need to, I think, stop screen share, na? This one, no? Now video is coming, no?
No.
No,
No.
I have joined in.
Okay. वो video actually 1 minute.
So it is showing in your display profile.
Okay. No. Okay. By double click, if you do, you can.
Yes, sir. It is not showing.
Participants, are you able to see? Can anyone say?
Yes.
You can double click on the speakers here. You will get found.
Yes,
So
video
one
is
question
visible.
from the participant that suppose if we don't have manual, can we download from your website?
Just wait, I will take a snap and I will share it. I think it's
Okay.
better.
Hello, Neeraj sir.
Yes, sir.
Murli, Karthik is asking, suppose if we don't have manual, can we download it from our
Yeah.
website?
No, you have just asked me also. I will share your manual.
As per our, okay.
Yeah. You just before that you just share your target number, yeah, project ID. I will give you your manual.
Okay.
One minute. Then how can I get?
Sir, am I audible now to you?
Yes. You.
Hello, sir.
Where is my screen? Yes, now my screen is visible, no?
Yes.
Yeah, this is your DB37 screw connector. Okay. You don't know this screw connector configuration, which one is your positive terminal, which one is your ground terminal. So you just need to open your system description here. Your positive terminal is number 1 and your ground is your pin number 20. Same for 2, 21, 3, 22, like this. For digital in for 16 to 31, this is your digital in. And for digital out, user defined voltage is required. 5 to 30 volt is required. But how can we give that 5 to 30 volt in which pin? See, this is your digital out. We have need to give 5 to 30 volt in pin number 18 and pin number 37. this thing is mentioned in your manual. So how here pin number 17 and pin number 36 is generating 12 volt user defined voltage. So in my card, in digital output, I have connected this 12 volt, this one, started from 17 to 18. This card I will use for digital out, and I have made this card for loop back for digital out to digital in. See, for digital out, user defined voltage DC supply is required, but digital in is not required. That's why here is a one cross mark. Okay, and next is facility for static digital IO. You can use as a static digital IO normally. That card, that block we are calling digital out block or digital in block. In this case, your in each sampling time either up or down. Each sampling time either up or down. That's we call digital IO. In this case, we can use this digital IO. But someone want to generate PWM signal using our Simulink, using our library block. That time you can use this PWM block. PWM IO means frequency and the duty cycle can be changed once per sampling time. According to that, you can generate this PWM signal. I show you in how can we use this PWM IO block and how can we use this digital IO block. And this is your timestamp IO. That means your signal profile can be changed once per sampling time. See, this is your signal like this, and here is your signal like this. Means duty, frequency, and full your profile signal profile is changed for sampling time. So this thing is mentioned in your system description, your system document. And this is your analog in block, and this is your digital in block. Analog out, digital out, same thing. I'll show you on at demonstration. So for this case, we have need to use this OP control block, OPCTRL block. Why we are using this OPCTRL block? Because FPGA is managing our IO card, right? To run this FPGA, some code is required. So that code we are calling bstream file. Yeah, bstream file. Yes, one is .conf file, one is .bin file. See, this is your bstream file, .bin, .conf file. And in .conf file, you can map your which pin will for digital out, which pin is for digital in. According to this data in port number, after that you place your slot 2 subsection module B subsection 1. Everybody have to know what the subsection 1 to subsection 3. Why it's not subsection 3 in analog out, yeah, analog in, but why it's up to subsection 4 in digital out, digital in. Everybody know what the subsection. Okay, already I explained this this subsection part. First, this is your block analog out block, and this is your analog in block. Analog in block, and this is your analog out block. After this is your OP control block. In OP control block, we have need to paste your bstream file .bin. this name is required, and also this bitstream file we have need to paste in our path, project path. And after that we have need to choose our board type. If board is 4510, then we have need to choose it TE0741. And the .conf file, we have need to open it, and after opening it will showing like this type of. Suppose for analog out, that data in port number is 1, we have need to place in data out port number is 1. So after placing this, you will see like this type of, which slot is your analog out, which slot is your analog in. Slot 2 module A subsection 1 is for analog out. Same procedure for digital IO card. You just have need to put this data output number. After that, you can generate your PWM signal. So here is your how to generate your PWM signal. For this case, you have need to use just a minute. I'll show you here where that IO block is available. In RTLab IO, we have need to go this RTLab IO, then OPAL RT common. It's depend on your model. If your model is like 5600 somewhere old version, then you can use it ML605EX1. So common. This is your analog IO, and here you can put that data output number, and here you can put that data in number. And this is the digital in. This is the digital out block. This is the PWM in generate. According to that, your frequency and the DUT will be generated. And this is your PWM out. You will give like frequency 500 kilohertz and the DUT ratio is 0.5. According to that, your PWM will be generated. And another one is your, this is your OP control block. You have need to paste your .bin file name, and you have need to choose that board type and OK. Okay, any question?
Sir, am I audible to you now?
Yes, yes.
Sir, actually in between I could not connect my audio. Sir, when we are using upcom block, I think it can support maximum number of inputs as 24 or 25.
You can use two upcom block. That acquisition group number should be different. Okay. Suppose your first upcom block, that acquisition number is 1, and second you are suppose your signal is more than 25 or 26. So that time, suppose total number of signal is 40. Next 14 signal, that acquisition group should be different. Okay.
So can you just show where to get that option, the model?
Okay.
So like this, how many acquisition group number we can give, sir? I mean, what is the maximum limit like that? For one block, we can go for 25.
Yeah. I think for 26 or 25, you can use OPCOM block.
25 is there, sir, as per my knowledge.
Huh.
If you have more than 25,
then you can use another one.
but that is not, I think it is not taking, sir. So that is my doubt actually.
It's not taking?
Yes.
Have you changed this acquisition group?
No, that I have not tried. That I will try.
Yeah, you just try it. and just after that you can contact with me if his is not working. We'll see.
Okay, sure. And one more, my query is, suppose if we do not have that white manual, whatever you're supplying, if
Okay,
you
you
purchased,
no, you
then-
have no need to purchase it. I'll share you in software. Yeah, soft copy.
Okay.
That manual.
So as per model number.
Yes, as per your simulator model.
Okay, sir. Sure, sir. Definitely we'll try to contact you
Yeah.
after this session. Thank you.
Yeah, another thing. So how to contact with our technical support team? Just go. Here is something I'm telling you. OPALRT.com. Then support. First is your knowledge base. You will get some error in your model at the time of building, yeah, at the time of execution, at the time of loading. You can sort your error here. Suppose here I get one error like compiler issue, compilation error. You can get whatever you paste your error, and you will get your solution here. If your solution are not available here, you can contact with our technical support team. Contact technical support team. And here you have need to first name, last name, mail ID, organization, market segment, application, and main thing important is your target serial number. You have to mention here and your problem, and our support team will contact with you. After you raise your ticket, our support team will contact with you. Okay. Suppose your manual hard binding manual is the last, you want to take from soft copy, you can contact with this procedure, then they will provide you your soft copy. Okay, any
Hello.
question? Yes, sir.
Yes, sir. After this question, if the participants is having any question, then we can take. Otherwise, you can take the lunch break now.
Yes, sir.
Anyone who want to ask the questions can raise your hand or unmute yourself.
Sir, one more query, sir.
Yes.
Sir, when we are running the model in that RT lab, for example, say in SIL mode, can we store the data in the RT lab workspace? Whatever
Yes,
the signals
you
we are
can
chasing,
store it
so
like
that we
using,
can plot the same data in the MATLAB.
yes. You can store it using that OP write file.
Sir, if possible during the demo, please
Yes, I
elaborate
will
it, sir.
show you. Yes.
I will ask once again.
Okay.
Okay, sir. Thank you.
Oh, that means you are asking for it's running in a MATLAB, not in a real time.
No, sir, in real time only. When it is
Okay.
running in real time.
Yes. I show you. After storing your data, I will plot it and I will show you.
Okay, sir.
Okay.
Thank
you. Any question?
I request participants, if they have pre-questions, then for the next session, please earlier write it and send it to Q&A so that sir will answer in a free manner. Okay. Thank you. Any more questions?
Okay, we'll meet at 2:15. We'll meet by 2:15.
Okay, sir.
Okay, 2:15 we'll meet. Okay. Okay. Thank you.